Her last name is Esther.
Yeah.
All right, everybody, I think I'm going to go ahead and get started, and welcome to Wednesday. And actually, this is our very last regular class meeting. Believe it or not, we have made it to the end. It's been quite a whirlwind. Remember, we started off with videos, and I was in Colorado freezing in my garage. I made my way back over here, and it's overall been pretty good to be back in person. I have to admit, I really enjoyed getting to meet my students face to face again. It's been wonderful in that sense. What we're going to do today is we're going to cover one last section of the book. It's going to take just the first half of the class today, and then once we've done that, we will be done with everything we need to know for the upcoming final. And during the second half of our class, I'm going to talk about the final. I'm going to go through the resources with you and make sure you are kind of oriented a little bit as to what you want to look at and where you can find it. And we'll do a little bit of sort of review. It's not really possible to review this entire semester in 1 hour, but we will at least try to get you started on getting your head around what you need to do for these next days ahead, okay? Before I get to that, of course, you just got your exam back. I think everybody has now gotten their exam back who's here right now. So I just want to let you know that, of course, the solutions are up in Canvas for that exam. I had a big range of how people did on this test. There were some really, really high scores. There was a number of people above 90%. And I can tell some people are just, it's making sense, right? It's just coming together here at the end of the semester. But there's also a group of us that have just really struggled to get to where they want to be, I'm quite sure. And so for those of you who did not do as well as you would have liked, first thing you should do is definitely take your exam side by side with the solutions and just really run through that and make sure, first of all, make sure that I graded it correctly. Somebody during my first class today already noticed that I had missed something on the scratch paper. And sometimes on the scratch, if you don't refer to your scratch paper in your test, then I don't really know that I'm supposed to go look in like the third page of your scratch paper or something in the back. And if I don't know that, I can actually forget to do it or miss it. So it is possible that I might have missed something. Or if you just don't know why you lost points or for what the reason was, or you just don't get it. You don't know why, how the problem was supposed to be done. Anything like that, feel free to take my solutions side by side with your exam and kind of check that off, check them side by side. And if it's still not clear, please do come to me. I do not bite. I'm happy to talk to people. Even if you're not sure, you're like, oh, I don't know, maybe I should have gotten more points for this, or I just want to know why I didn't do as well as I wanted to here. We can talk through anything. I really do want everybody to have a good feeling. Obviously everybody's going to make typos, even myself. I had a typo in my own solutions. I had to go back and fix later. Those things happen to all of us. Doesn't matter how much you study or whatever, you're going to have that happen. I try not to be too harsh on that. But still, you may find that you want to, again, check the answers to make sure. But then, yeah, if there are some more substantial things that you just really haven't quite got sorted out yet, feel free to drop by and chat with me, either in Zoom or in person. I'm going to have office hours almost every single day for the next week, just to really be available, get you guys ready for the final. I encourage you to take advantage of that. Always want everybody to do well. I want to help out as much as I can. Doesn't mean it's easy. Doesn't mean that we don't have to put any work into this. We definitely do. But I'm also working really hard, and I'm here for you. I'm going to support you as best as I can, as much as you're willing to to take it. So just let me know. Right. So I think everything is up to date in Canvas. The only things left that still have to happen are we have one more homework assignment, which is just 2 problems. It's going to take you 30 minutes, maybe. So it's not a long assignment at all. Probably takes 1 sheet of paper to write the whole thing up. It's just got 2 problems on it, just based on what we're going to talk about right now. So that's due on Friday. After that, I will be dropping your 2 lowest grades from the homeworks that we've had for the entire semester. I will drop your 2 lowest ones. I'm ultimately going to re-weight your grade. Don't forget, whatever the percentage is that it says on Canvas right now is actually lying to you a little bit, because your percentage is actually better than that, because I have to remember what I'm going to do is I'm going to downweight whatever part of your grade was the lowest, whether it was one of the midterms or the homework, or it could even be still the final. I downweight that 5% and I upweight by 5% whatever you did the best on, whether it was homework or midterm or final, whatever. And so when I do that, it actually pushes your grade up generally about 3 or 4%. It's a little hard to say, but I can't do that adjustment until after the final is over, because that's one of the components of the grade.
And that means if you just try getting a 0 on this homework assignment and your exams end up being better than your homework, you're gonna weight the exams better.
Well, no. I'm talking about the entire homeworks for the whole semester, not just one homework assignment.
Yeah, but if I try.
You could. I really don't get it.
If I homework assignment, you get a 0, I'm gonna get dropped.
Yeah, I'm just gonna drop.
That's right,
So you
dang
need
it.
3 zeros on a homework assignment to do what you're trying to do.
Yeah, that sucks.
Well, in that case, yeah, I mean.
I've submitted some late, I could probably argue.
Don't listen to this guy, basically what I'm gonna say. I don't. You should always try to do the best you can on everything. That's really my advice. Then everything will work out to your maximum benefit. But anyway, I just wanted you to know that if you're looking at that spreadsheet, kind of looking at where you stand, there is that adjustment at the end that I can't do until after finals. The Canvas page that is up on our website, we're going to look at it in a little while. I just wanted to also let you know that I will be taking that page down on around June 1st. So after next week, we have the final. It's going to stay up all through finals and probably even for another week after that. I will be taking it down eventually. So if you really want to, one day in the future, wallpaper your house with solutions of Dr. Annan's from all of the math that you learned in this class, you should download anything you want to have and keep in the next couple of weeks, just so you can have it for the future. Your exam solutions, group works, whatever, because that will be coming down off of Canvas eventually. So just wanted to make you aware of that as well. Okay, so I think before we talk about the final and sort of the big picture of the semester and everything, I do want to cover one last section today. And this is section 9.6. It's the last section of the Math 250B curriculum that I'm required to cover. And this is called Non-Homogeneous Linear Systems of Differential Equations. Okay. So what we're going to do here is the following. We're going to go back to consider this linear system. So I think everybody is probably kind of tired of looking at this. This is just x prime equals ax. But what we're going to do today, guys, is we're going to make this system non-homogeneous again. Right at the start of chapter 9, I had put this plus b term on the right-hand side of my linear system here. And today we are going to come back and focus on that. So here, for the first time, we're going to really focus on a situation where the b is not 0. And that means that you have this non-homogeneous linear system. And the goal is to solve for x. So to solve for x, we are going to follow 3 steps. Okay, so I'm going to give you the outline here and then we'll talk about the steps. So we're going to follow 3 steps here. The first step is By the way, these 3 steps are going to sound very familiar. The first step is going to be solve the corresponding homogeneous linear system, right? So we're going to solve the corresponding homogeneous linear system. That would, of course, just be the system x prime equals ax. So we just ignore the b. So we ignore the b for the time being. So we solve the corresponding homogeneous linear system x prime equals ax for the complementary function. It's the same word that we used back in chapter 8. Complementary function, and that complementary function is written x sub c of t. Okay, so that's just the first part. So we find this complementary function. That's the step 1. So that just means we go back and we do the stuff we learned last week. We find the eigenvalue, eigenvector pairs. We build those basis solutions for that homogeneous linear system. So this is called the complementary function. That's the first step. So we already know how to do step 1. That's what we learned last week. Now, step 2 is the new business. This is where we're going to find one particular solution. One particular solution. I'm going to write this as x sub p of t to our full non-homogeneous system, x prime equals ax plus b. So we just have to find one solution there. And for this, I'm going to say see below, because in a moment, I will explain how to do step 2. That's really the new material. So we'll come to that in a moment. But then finally, the third step, what do you suppose the third step is?
Combine.
Take the complementary function and the particular solution and add them together, right? That's exactly what we've done in the past. So the general solution here on step 3, right? The general solution, this would just be x of t equals x sub c of t plus x sub p of t. That would be the final answer. Okay. And so this actually is just the same 3 steps that we would have used to solve in chapter 8 a non-homogeneous single differential equation, right? And guys, if you put boxes around your complementary function and your particular solution, and you just want to leave step 3 like this without recopying everything, that's also fine. Just like it was fine before, I don't mind you doing that here as well. Okay. Everybody with me on this? This is the 3 step. We just have to explain step 2. In order to really explain step 2, I'm going to start off with just a quick note here about something that this will help lead into how step 2 is going to work. This complementary function, right? So when I write the x sub c of t, of course, we already know what that looks like. Yeah, that is a linear combination of the basis solutions to this linear system. So this is going to look like c1 times x1 of t plus c2 times x2 of t and plus dot 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 plus cn times xn of t. And this is just a linear combination of a basis for the original homogeneous system. The n that you see in the expression here, that's just the size of the matrix A, of course. A is n by n. So you have an n by n matrix A, and so therefore your system just looks exactly like that. Okay, this makes sense? Great. Well, it turns out that what we can do, and we're going to need to do this, is that we are going to form what is called the fundamental matrix. So just as a little definition here, I haven't used this word before, but today I'm going to use it a few times. We're going to form something called a fundamental matrix. And what that is I'm gonna write it as a big X of T. It is a matrix that you're simply going to put the columns, you're gonna fill the columns of that matrix with these X's, X1, X2, and dot, 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 up to Xn of T. So this is called a fundamental matrix. And I do want to note something about the fundamental matrix. I want to note that this, that's okay. So this fundamental matrix, this is invertible. So guys, all we're doing is we're just taking the solutions that we found in step one and we're laying them directly into the columns of this bigger matrix. Can somebody tell me why is this matrix invertible? Why will it be invertible? It's probably not a bad time to remind you guys before the final exam that there is a invertible matrix theorem in the back cover of the book that goes A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, I think. All right, we did a ton of things from that list. And so there's a bunch of stuff in here about determinant not being 0. The rank should be N. There's things about null space and blah, blah, blah. But there's another one in the list which says that the columns of the matrix are Li. Now, these X's up here, they are a basis for the solutions to the original homogeneous system, right? So these X's, X1, X2, X3 that I put in the columns, these are Li because they're a basis. If something's a basis, it's got to be a spanning set and it's got to be Li. So if I've got linearly independent columns, I've got an invertible matrix. Okay, so I'll just say here, since columns are Li. So that's the reason. If you want a sort of a theoretical reason for it, that could be the reason. Yeah.
That big X is not the same thing as X of T is equal to C, X plus C, X of C plus
No, this is a little X here, sorry. Yeah, maybe I need to like fancy up my X here. Yeah, this is a capital X that we're talking about there. That's the fundamental matrix. Okay, great. Everybody okay so far? I have not yet explained step 2. I've got step 1, basically, that's this part, the complementary function. And I'm putting it into this fundamental matrix now, right? But the thing I want to note is that we can now write this complementary function in a little bit different way. And I think it's worth showing it to you. This complementary function can actually be written as capital X times, well, let me start by writing it as just a column vector here, C1, C2, and dot, dot, dot down to Cn. Let's just take a look at that real fast. If you actually sort of look at this as a matrix multiplication, so I have x1 of t in the first column, then I have x2 of t, and so on and so on. The last column is xn of t. And I multiply that on the right by these CNs here, these constants. Then see, when you do matrix multiplication, right, I think we all understand, by the time we get to the end of 250b, we should understand anyway, how to multiply these together, right? We go across the rows of the matrix on the left and dot those with the column on the right. Do you notice that the C1 only ever feels the X1? When you multiply this out, this C1 is only going to feel whatever's coming from the far left. And then the C2 feels the stuff in the second column. The C3 feels the stuff in the third column. In other words, it's exactly this. C1 gets multiplied by X1. C2 gets multiplied by X2, and so on. This is just another way of writing the complementary function. And in fact, I'm going to abbreviate it even a little bit more, and I'm just going to write it as X times C. So that is literally the complementary function kind of written as a vector equation, as opposed to writing out the whole thing as a linear combination. But it's the same thing. Okay, so if everybody's good with that, now I can talk about step 2. Sebastian.
Is that kind of like the new AX? Or kind of like how we had X prime equals AX, now we have X T equals.
I would not say that this is related to this. No, because here we have X prime, whereas over here, we're not really looking at the derivative, right? We're just looking at this is just sort of a symbolic representation of my complementary function. So at this point, we don't have the plus b yet. Not looking at that. And we're just saying that if we want to solve this part, the homogeneous part of my linear system, this is what the solution is going to look like, or this is how we can write the solution. So it's not really that we have a new, it's not like we're changing our original system. We're just representing the solution to that system in a vector equation here. That's basically what's going on. It's a good point. I don't know if I'm getting to the heart of what you're thinking about, but are we okay so far? Anybody else have a question so far? So are you ready for this, guys? We're going to talk about step 2 now with that kind of background there. So for step 2, we will, one last time in Math 250B, we are going to guess what the particular solution should be. We will guess the particular solution. I'll put a colon here in a minute. I'm going to write down what we're going to guess. So we're going to guess what this X sub P of T should be. Okay. Now, you guys don't need to write this down. I'm just going to scribble in the corner for a minute. You remember when we were guessing what the particular solution was supposed to be for the variation of parameters method in chapter 8? We were guessing, what was it? U1, Y1 plus U2, Y2. And then ultimately, you know, U1 and U2 were to be determined, and we did determine them. By the way, you guys did a great job on the exam of knowing your formulas. Everybody had the Y sub P and the U1 and the, I don't think I couldn't find any typos or errors with that at all. That was really well done on that variation of parameters problem. The way that you get this though is you started up here with the complementary function, which was C1y1 plus C2y2. Remember that? You have a linear combination of y1 and y2, and then we did variation of parameters. In other words, we changed the parameters C1 and C2 into U1 and U2. So guess what I'm going to do here? I got exactly the same idea. I have X sub C as big X vector C. So here I'm going to do big X times vector U. I'm going to put that in a box where U is to be determined. So this is literally just mimicking what we would have done back in chapter 8. We're now going to do the same thing in chapter 9. We're going to take the complementary function, which is X times C, and we're going to do what's called variation of parameters. We're going to change the C to a U. And then we're going to try to solve for U. Make sense? By the way, guys, there's only 2 new equations you need to know today for this material. The rest of this you can kind of let slide under the rug if you aren't interested. The 2 equations, this is the first one. Okay, we need to know that the particular solution is big X, which is the fundamental matrix, times U. What do I do every time I think of a guess for a solution and I want to work on it and check it out? What do I usually do with that guess?
plug it into the original.
Plug it into the original problem and try to make the left side and right side match up. That's exactly right. So let's do that. Let's plug in to x prime equals ax plus b. And let's just see if we can get it to work. We're going to plug that thing into our linear system. Now on the left side, I'm supposed to take the derivative of x sub p. Well, this is a product, right? This is big X times u. So I'm actually going to use the product rule to take the derivative of it. So on the left side, I'm going to have big X, first term times the derivative of the second, which would be the u prime, and then plus the derivative of the first term times the second. It's like that. That's just the product rule on the left side. I'm taking the derivative of this box. First term times the derivative of the second, plus the derivative of the first term times the second. And then on the other side of the equal sign, I have to put big A times x. So here's my x, which is big X u. That's a big X. And then we have a plus b there. So is everybody comfortable? They understand what happened? I took this box. On the left side, I put the derivative of the box. And on the right side, I plugged the box in for the x in my linear system right here. So I did the same thing on both the left side and the right side. Now, do you have a little space, guys, where you could just do a little bit, don't get in the way of your calculation here, but I just want to do a little bit of scratch over here. Okay, so let's not get this mixed up with our beautiful derivation that I'm in the middle of here. I would like to actually work out, I see the x prime right here. I would actually like to figure out what that equals. I just want to kind of on my scratch paper figure that one out. That's just the derivative of this matrix. So that just actually means that I'm going to take the derivative of everything in the matrix, right? So this is just going to be the derivative of x1, the derivative of x2, and dot, 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 all the way up to the derivative of xn. Okay, so we're just taking the derivative of every single column, which means every single slot. Now, does anybody know what x1 prime is equal to? Just x1 prime. The x1, what was x1? That was a solution to in the complementary function, which means that it actually was a solution to the corresponding homogeneous system, right? That's what x1 was, and so and also x2 and x3 and so on. So what is x1 prime equal to? A x1, right? There's no plus b right now. We're just looking back at the complementary function. So the x1 prime is just a x1. And x2 prime is just a x2. And so on, dot, dot, dot. And the last column is a xn. That's all you have. That's all you have. Now, what's your knee-jerk reaction here, guys? What is this begging you to do right now?
About the A.
Yeah, factor that a out in front. Exactly. I'm going to put the a out in front. And after I've factored that out, then the rest of my matrix is just the x's again. Is everybody able to see this okay over there? Okay, so this is just a times all of those columns. But guys, that's just a big X, right? This column of the x1, x2, x3, and so on, that's just the big A, big X. That's all it is. All right, so guess what I'm going to do? I'm going to take the big X prime and replace it with big A, big X. Oh, wait a minute. Look what I got here, guys. On the left side, I've got the X prime times U, and on the right side, I've got big A, big X times U. Aren't they the same? Right? We just sort of said that they're the same. Let's cancel them. Let's just cancel those things. They go away. It's getting simpler by the minute. Getting this thing simplified down. Okay, so we just cancel that. So then what are we left with? Oh, we're just left with big X times U prime equals B. The big X U prime is equal to B. I bet I could solve that for you. I've already said that big X is invertible. So this big X right here, I can invert it to the other side of my equation. Okay, so just to be really clear, we have just this is all we have, guys. This is all we have right now. The big X, oh, sorry, there's a U prime on that. Big X times U prime equals B. Let's just throw the big X to the other side of the equation. That means it's going to be big X inverse times B, but that's what U prime is. And so what am I going to need to do if I want to get U? Say it again. Integrate it. Exactly. I've got the derivative of U right here. So if I want to figure out what U is, I just have to integrate it. Yeah, that's exactly what I'm going to do. U is going to be the integral of X inverse times B. And this, my friends, is the second of the two new equations that we need to learn for this section. Actually, this is the whole story. This is everything we need to know. For step 2, if we want to find one particular solution, I can tell you how to do it. Write down your fundamental matrix and multiply it by U, where this is what U is. Yeah. Nick.
That's with respect to T, right?
Everything with respect to T. And when we do an example, I'll definitely emphasize that. Yeah, T is the variable that's hiding throughout. I mean, over here, I didn't really hardly write very many T's on the board at all, but everything is a function of T here. That's exactly right. Okay, is the derivation okay? This is the theory of it. If you don't like the derivation or you don't want to think about it, just make sure you know there's 2 boxes right here and you can't go wrong. Okay, so let's practice. Let's finish up the first half of our class with an example of an actual system. This is a non-homogeneous linear system. That's what we're talking about today. All right. So here's an example. Find the general solution. Find the general solution to, let's see, X prime equals AX plus B, where, let's write down capital A. Capital A is going to be the matrix 2, -1, -1, 2. And then I've got to put a B vector in here. The B vector is going to be the vector 0, and then 4e to the t. Okay. So we're going to try to solve that using what we've just learned here on the first part of our lecture today. So, of course, the first step of the process, we're not even going to look at the B. We're just going to look at the big A, and we learned how to do all that stuff last week, right? So we just have a little 2x2 system here. And so for the solution, what is the very first thing we're going to probably try to figure out?
No, complementary.
Yeah, the complementary function, but how do we get the complementary function? What are we going to, let's boil it way back to the very beginning. What's the first thing I need to do?
Get the eigenvectors.
Find, even before I find the eigenvectors,
Values.
the eigenvalues come first, right? I've got to find the eigenvalues. So that's exactly right. We're going to do the determinant of the matrix that we get when we subtract lambda off of the main diagonal. Okay, so it's a 2x2, so I don't mind just using the 2x2 formula. 2 minus lambda times 2 minus lambda minus 1. And if you multiply that out, you'll get lambda squared minus 2 lambda minus 2 lambda, which is actually minus 4 lambda. And plus 4 minus 1 is actually plus 3. And This actually factors very nicely, lambda minus 3 times lambda minus 1. Okay, so got a nice little factorization there. So I have two lambdas to work with. Let's start with, I'm gonna do this part fairly quickly because we've done a lot of these little null spaces already, but for lambda equals 3, I have to take the null space of the matrix that I get when I subtract 3 off of the main diagonal. Well, that's just a matrix of all negative ones. Negative 1, negative 1, negative 1, negative 1. This matrix is never invertible. I can always cross off a row. And then I'm gonna just do my little trick where I swap the entries from the other row. This is this A-B switch trick thing that I've done a few times. And I'm gonna switch the sign of the 1. So that means it'd be the negative 1, I mean. So I have a negative 1, but I change it to a 1. So there's my vector. If you don't like that, of course, you can still set up your free variable, solve it by back substitution, and then bust out that free variable to get your basis vector. But here, I don't mind just kind of doing it quickly in my head. So my first solution, I'm going to call it x1 of t, would be e to the 3t times the vector negative 1, 1. Go ahead and put that in a box.
Yeah, that's not xc of t.
No, this is just x1 of t. That's just the first solution. That's the one right here. Okay, that's x1 of t. So far, so good? Let's get the other lambda. Lambda equals 1 is my other eigenvalue. I'm going to do another null space here. So I have to subtract 1 from the main diagonal of the matrix. And again, the two rows are multiples of each other. I'm just going to wipe one of them off. And I'm going to come over here and I'm going to make my eigenvector. For this eigenvector, I swap these two numbers and I change the sign of one of them. I'm going to change the negative 1 to a positive 1. And so my eigenvector is just 1, 1 this time. And so I get my second solution, which will be e to the t times 1, 1. Okay, so there's x2 of t. And so actually, I now have my two basis solutions for the 2x2 homogeneous system. Okay, so I can actually write down the x of c now. In fact, I've set myself up to do it right here. Let me see if I can put it right here at the top. X of c of t, here's the formula, right? C1 times e to the 3t times negative 1, 1 plus c2 e to the t times 1, 1. There is the complementary function. Okay. So far, so good?
Mhm.
That's step 1. That's everything we need for step 1. Okay. So now we're going to talk about the new part. The new part is where we do the particular solution. I've got the formula right here. Notice that it relies on big X. I would recommend that we write down big X next. Okay. So the big X, how does that work? It's right here. We just build the solutions that we just came up with. The x1 and the x2, we just put them into the columns of big X. Okay, so let's try and write that down. Try to write down our fundamental matrix here. Don't really need much of this anymore. Let's go ahead and clear this off for now. Right, so thus what we have is big X of t equals. So the first solution here, guys, goes into the first column of the matrix that I'm going to write down. I would recommend that you're going to want to multiply this e to the 3t into the entries so that you have an actual column there that you can put right directly into here. So what that's going to look like is going to be minus e to the 3t and e to the 3t. That's just your first column of the fundamental matrix. And then the second column, I do the same thing with the x2 solution, and I just get e to the t and e to the t. So there it is. Okay, so that's my fundamental matrix. Very important part of this process we're talking about today. Now, ultimately, I will multiply that by u to get my particular solution. But I gotta figure out what u is. And that's where this comes into play, right? The u, right, the u is gonna come from here. And notice that I need the inverse. I gotta have the inverse here. So I gotta take the inverse of this matrix. The inverse of this matrix. This is not a bad time to review something for our final that we will want. I'm gonna put it over here. If I have a 2x2 matrix, does everybody remember how to do the inverse of that without even having to break a sweat?
1 over determinant times matrix.
Okay, 1 over, okay, so very, very fast. Let me see if I can get up here and write it down. I take the determinant of the matrix, which is AD minus BC. I put that on the bottom, and then I just, if you remember, we play with these numbers here, right? The D and the A get swapped, and then we put minus signs on the B and the C. Right, so there's your formula. Now, somebody asked me in the first class, would I maybe ask you to do this for a 3x3? There is no nice formula for a 3x3 inverse, right? We have to actually do a lot of work for it. And we're not even talking about a 3x3 of numbers anymore. We're talking about a matrix that has functions in it. So it's going to be a mess, right? So I'm going to hereby promise you that you will not see on a final exam a 3x3 non-homogeneous linear system. However, if you were interested in doing that at some point, the way you would want to do it would be to do a more general formula for the inverse of a matrix. I'm wondering if anybody remembers what the, because this is good review for the final. I might ask you this for a matrix of numbers. And you look like you want to tell me what it is now. There we go. 1 over the determinant of A, which is really matching up with this thing here. And then this matrix here gets generalized to something that I call the adjoint of A. ADJ of A. Does anybody remember this? This goes way back to February, right? We did this way back before the first exam. And the adjoint of A, in case anybody needs a refresher on that, which would certainly be understandable, this is simply the transpose of the matrix of cofactors. So, so worth remembering that. You know, it's something I might ask you about.
That's so horrible.
Well, this is a very clean looking formula. The problem is that the matrix of finding cofactors is kind of a pain, and you got to find every single cofactor of the whole matrix. So it is definitely a lot of work. Suffice it to say that for this section, 9.6, I will only ask you for 2x2s. Okay, so let's just do it right here. I'm going to do 1 over the determinant here. Now that's AD minus BC. So A times D, we have e to the 3t times e to the t, which is actually e to the 4t. There's a minus on that. And then I'm going to subtract another e to the 4t. So by the time you're done doing that, you will have actually subtracted 2 factors of e to the 4t. Right, and then we swap the diagonal entries, so the e to the t and the minus e to the 3t, those get swapped. And then I put minus signs on the other 2 entries. So let me get this over here. Right, so there's the formula for the inverse of the fundamental matrix in this case. So far, so good? This scalar that's in front right here, you are certainly welcome to multiply it through the matrix. You can always do that. But it's just going to put a lot of fractions into the matrix, and it makes it messy, in my opinion. I would rather just leave it like that for now. Okay, so I'm just going to leave it like that. And then what do I need to do with it? I need to multiply it by b. So finally, we get halfway through the problem, and we finally are going to start talking about the b right here. Okay, so let's do it. So what we're going to do is take x inverse times b. All right. So this is gonna give me 1 over -2 e⁻⁴t times e to the t, negative e to the t, negative e to the 3t, and negative e to the 3t. And I'm gonna multiply that by the b vector, which is 0 and 4e to the t. So this is gonna test your matrix multiplication a little bit, guys. It is gonna test that because we're gonna be seeing these kinds of expressions. Okay, so I have out in front, I have negative 1/2 e to the 4t. And now I'm just gonna multiply this. Go across the rows there and down the columns here. This is how we do matrix multiplication. All right, so we're gonna get a column here. We have 0 and then minus 4e to the 2t. And then on the bottom row, we're gonna get minus 4e to the 4t. Okay. That look all right? The next thing I'm gonna do is integrate that, but before I integrate it, I actually now think it would be good to distribute this scalar inside the vector so that we have just two simple expressions to integrate. Notice that a lot of stuff simplifies. 4 divided by 2 is just 2. The minus signs all cancel. And I have to be careful with the exponents. E to the 2t divided by e to the 4t is actually e to the negative 2t. So we get 2e to the negative 2t in the top entry. And then on the bottom, we literally just get 2, actually. It's quite simple. Okay, so that's what I get when I just kind of simplify the expression. And now I'm ready to write down what u is. U is the integral of x inverse times b, which means that we are integrating the vector 2e to the negative 2t and 2. And this is with respect to dt. Okay, so Nathan was asking me earlier whether there's a t here. Yeah, this is dt. And guys, you're just simply going to integrate both slots. Kind of just integrate both slots, right? When I integrate 2e to the negative 2t, I just have to use, what is it, just the u substitution basically, right? If I just I'm just gonna let u equal negative 2t right here. I'm gonna do a little u substitution. And when I do that, I will actually get negative e to the negative 2t. When I integrate that one, what do I get when I integrate 2 to t, right? There you go, there's the antiderivative there. I always get asked the question, do I need to add the plus c? You know, this is an integration, it looks like an indefinite integral. Normally, yeah, you would add a plus c to this, but we don't need to because we're just finding one particular solution. I don't have to find all possible choices of u. I just need to find one choice of u that works. So let's just use this one, right? There's no need to make it more complicated than that. So I'll just forget the constant, basically. Okay, so that is my u. And so now I can do the x sub b. It's big X times u. And I'm running a little short on space here, but I'm going to try to make this work. So the big X, I've got it up there at the top left of this board, minus e to the 3t, e to the t, and then e to the 3t, e to the t. And then the second column, I have minus e to the minus 2t and a 2t. So I just have to multiply x times u. I think I'll just come over here and do that. All right, so now I'm just literally matrix multiplying again, right? So I go across the rows of the first matrix and down the column of the second matrix here. So this is going to be e to the 3t and e to the negative 2t. That multiplies to just give e to the t. And then plus 2t e to the t. All righty, and then on the bottom row, I will just have a minus e to the t plus 2t e to the t. Looks just like that. And that's my x sub p. Looking okay? I like to put a circle around that. Whenever I get my particular solution, I put a circle and so I can keep track of it. I've got my complementary function right here. I've now got my particular solution right here. And the last step then, of course, is just to add them together. So step 3. This is where we just write x of c equals, sorry, x of t equals x sub c of t plus x sub p of t. Again, you're allowed to just write that and just call it good. Because you're just literally going to be rewriting what's already here and here. But I do want to actually show you one time when I actually plug it in. Okay, so I'm actually going to write it down. C1 e to the 3t times negative 1, 1 plus C2 e to the t times 1, 1 plus this thing right here, e to the t plus 2t e to the t, and then on the bottom minus e to the t plus 2t e to the t. And that would be your final answer. Okay, so just to see what it kind of looks like on paper. So we get one extra term here that's now being added on because it's a non-homogeneous system. This makes sense to everybody? Any questions about that? So what are the two important equations? This is the first one. We need to know this. The particular solution is x times u. And then the second equation, u is to be determined. Well, we determined it, right? We determined it. It's simply the integral of x inverse times b. If you know these two equations, you can do the whole process. It's a little long. I can pretty much guarantee there's going to be one of these next week because they actually allow us to review a lot of material. And I like that. One of the things I've always liked about 250B is the way it brings everything together at the end. I mean, is there anything in this class that we didn't have to touch here? We did null spaces, determinants, eigenvalues and eigenvectors, writing a general solution, taking the inverse of a matrix, multiplying matrices together, and so on and so forth. So there's a lot of stuff.
You didn't do orthogonality.
No, of course not. Not everything. I didn't actually mean for you to answer that question. I knew you'd come up with something. Yes, okay. Raylene, yeah.
Sorry, I'm probably getting confused with something else.
It's okay.
You put find the general solution, so how do we know what to use? Isn't there like another method to find the general solution?
Well, the word general solution is very vague. Yeah, it's very general, right? It's used all the time. We used it in the first week of the semester when we said things like, oh, find the general solution to, I don't know, y double prime plus 2y equals 0. Find the general solution to that, right? So this is a completely different differential equation, but we can ask the same question about it, right? We can ask to find the general solution to it. So you've heard that phrase. This phrase is certainly not new, right? But we're seeing it again and again and again, and we just have to recognize that we're finding the general solution of a non-homogeneous linear system. That's where today's lecture is sort of informing us how to do it. We have to recognize that we have a non-homogeneous linear system. Actually, when you stop and think about it, about half of what we've done this semester could be summarized as solve the differential equation, right? And we have learned so many different types of differential equations in different contexts. Some of them have been homogeneous, some of them have not. Some of them have been first order equations, some of them have not, right? Some of them have been functions you can annihilate, some of them have not, right? And you have all of these different categories of differential equations, and half of the battle, and we're going to practice this after the break today, half of the battle is identifying which type of problem is it, so that I know which tool to pull out of my toolbox to solve the problem with. Yeah, that's exactly right. Nathan?
Going off your comment about is there nothing we touched, is it chapter 5 going to be on the final?
Yes, yes. So let's do this. What I actually want to do is talk about the final after we take a break. So before we do that, are there any questions about anything we've done up here so far? Pretty straightforward. You're gonna have a chance to practice 2 of these just to run through for the homework for Friday, just to kind of get it into your blood a little bit and make sure you understand how to do that. And then, yeah, next week, very good chance I'll ask you to do 1 more on the test next week. So. Okay, let's take a break until 3:05, and then we're gonna be back and we're gonna start reviewing for the final a little bit. So go ahead and take 10 minutes and grab some fresh air if you'd like, and we'll meet back up here shortly. It's warm in here today. Yeah, that's a little bit. Those are just so fun that it's like you don't want to skip it. Yeah. No, I've never gotten something. Oh, yeah.
Because I already filed my forms lately, like when you're doing it, I guess I put I'm not doing something else. I know, but you can't do it. You can't order up classes. Maybe you probably need to send me. You just go right before this midterm. The Apple classes are not free. Actually, I think I was there. Anything else in the class? No, no. You sent me English last year. No, maybe. I think that was December. It comes back in your AI class. Yeah. It's already been months. Came back from the class. I was like, oh, well, how would you find this? And Paul was like, it's really windy outside. The trees are really. Trying to walk over here, yeah. Oh my god. Spanning tree here.
As long as it doesn't start a bunch of fires, I'm okay with it.
That was one of those spots. Yeah, take for credit.
Relax.
It's just doing
Here, or maybe mine was that, and then it was just online.
Yeah.
All or nothing with that.
But if you're only kids, you know.
Maybe isn't it?
Yeah.
Is it actually cold out there?
Yeah, it is.
Because I'm really hot in here.
Oh, yeah, you barely walked out of your fridge.
Oh, wow, okay. Good to know.
Look at this performance.
Oh, I'm so glad I didn't have to teach on Monday. I don't know, but did I tell you guys I'm going to Africa this summer?
What?
I didn't. Oh, yeah, I've never been there. I'm going to try to climb Mount Kilimanjaro, which is the tallest mountain in Africa. It's one of the tallest mountains in the world, actually. And of course, they have all these diseases and stuff. And so I had to like go get all these extra vaccines. And then somebody actually said, well, you really should get another COVID shot too. So actually on Sunday, I've already had several. This is already my second booster shot now of COVID. And so I don't know, you guys probably couldn't tell because you're taking the test, but I was really feeling lousy on Monday because you know, the day after you get the shot, sometimes for some people, there's a reaction. I had this splitting headache. And I was like, thank goodness I don't have to teach. But anyway, it all passed by yesterday. I felt great. Hopefully I'm good to go. Now I just have to climb up to 19,000 feet and see if I can do it. It will be interesting. So that's gonna be in July. But, we've got a couple things to do before we get to July, so I'm already thinking about summer too. You guys probably are too. Yeah, so what I want to do is spend the rest of today just kind of getting us a little bit oriented for the final. Guys, there's no way that I can fully like do a comprehensive review in what, 45 minutes? It's not going to happen. I just want to pinch you here and there with a couple of little things that maybe will start the wheels turning on your studying process and get you to have a little bit of a feeling what you're going to do. This is our Canvas page. And as always, there is a folder. It's called Final Exam Resources. And I put it right here. You see the files that are there. As always, there is a sample final and the solutions to it, which I highly recommend. I don't know if you've noticed, the exams kind of are similar to the sample exams. So if you look at the samples, I think it's a good idea. And before anybody asks me, because everybody always does, they want to have a second sample. So I will send you another sample final as well. So you'll have a couple of those. Also, there is well, let's look at the review packet. I'm actually going to open it up. The final review, that's this one right here. Let me click that open and we'll take a quick look at it. This thing blow up. Hopefully you guys can read that. Okay. Okay, so really quick, our official time for our final is on Monday from 1 to 3 o'clock, right? So in theory, you should all be available at that time. Now, if for some reason you would prefer to take the exam on Wednesday instead, I will allow that. That is totally okay with me. It's also from 1 to 3. It's also in this room. So that I don't mind that at all. If everybody decides to come on Wednesday at 3, and if we run out of chairs, I will start taking bids for the highest bidder for taking the seats that are left. So be sure to bring some cash. No, I'm just kidding. I'm just kidding. I will solve that problem. If there's too many people like all coming on the same time, I'll get a second room and I'll work it out. It's not going to be that busy around here. So, but anyway, yeah, you'll have the choice. You can come either Monday or Wednesday from 1 to 3. So kind of look at your final exam schedule, like what's going to be more convenient for you. If you want to get it over with on Monday, that's great. That's when you're officially supposed to come. But if you don't come on Monday, you're welcome to come on Wednesday and take that. It will be 2 separate tests. I will not be giving the same final, but it will be very equivalent in difficulty. I know it's hard to do that perfectly, but I'm going to do it. I'm just going to do it. So there'll be two similar finals, but they will definitely not be the same. There might be a slight difference in what they cover as well. Does anybody have any questions about that part? That makes sense? Okay, so, and I'm gonna give you a little extra time, you know, so if it's 3 o'clock and you're like, oh, I need a few more minutes, that's fine. There's not gonna be any cram to get somebody else in here at 3, I don't believe, so should be no problem. Let's see, same rules as we've always used, no books, no notes, no calculators. I will make sure that the numbers are reasonable. This is not a test where I'm trying to test your number ability. I'm not trying to test whether you can do derivatives and integrals. I've never really been testing that. That's really not what this class is about, right? We obviously have some integrals and some derivatives that we have to do. That's not the focus of what we've learned in this class. So I will supply a table of integrals, of course, and that will also have the annihilators on it again. And I'm also going to give you those Gram-Schmidt formulas. Can somebody remind me, what is the Gram-Schmidt process used for? When do you use it? Somebody besides Nathan. Jesus.
Orthogonalize?
Yes, to orthogonalize a set of vectors, right? If I give you a list of vectors and I want you to give me an orthogonal basis or whatever, that's when we would use the Gram-Schmidt process. So chapter 5, which is on inner product spaces, is something we have not reviewed since before spring break. that is an area that probably all of us should spend a little bit of our review time. Like, I don't think we need to spend a lot of time like doing more 2x2 linear systems. So we've been doing that, finding eigenvalues and eigenvectors. That's really fresh, that's really current. But some things like the Graham-Schmidt process, right, and other things from chapter 5 might be worth looking at again, because we really just haven't touched on that as much. I'll come back to the review sessions thing in a second. Let me scroll down a little bit, take a look at my extra office hours. Guys, for the next week or so, this is my priority, right? I am basically trying to be really available. You can stop by in Zoom, you can come in person. If you just need a little, discipline to get some studying done, right? You can come in to just hang out there so that you're kind of focused and don't get too distracted by other things. You don't even have to study for my class. You just want to come in and study anything. I don't really care. But I'm around Friday, Saturday, Sunday, Monday, Tuesday, Wednesday. It's basically every day that we have till the final. Yeah, so what I say down here is please review the previous review packets. I'm not going to make a massive new review packet right now. I mean, you already have so much to look at. If you think about it, you have what? You have 3 versions of all 3 midterms. Because for each midterm, there were 2 samples, and then there's the one that you took. That's 3 exams, and there's 3 that's already 9 exams, right? That's way more than you need to be getting stressed out about. So I don't recommend, that I don't think I need to give you a lot of other things to look at. Let me see what else did I think I put down just some advice here. You might want to glance, take a sort of center yourself with your studying. It might be worth just quickly going through the lecture notes. I don't mean spending 20 hours on it. I mean kind of scanning through them, kind of just flip through, remember what it was. It might trigger some things. Oh, and I would recommend that you have a piece of paper somewhere that is a to-do list. And on that paper, when you think of something that you realize, oh, I need to review, row space, null space, column space, you just jot yourself a note so that you remember to go back and look at it. I would take a piece of paper and do that because there's just so much stuff. If you just try to kind of remember what you're supposed to do, I could see some things slipping through the cracks. So I would do that. So you might review your lecture notes and maybe you'll jot a couple things down on that to-do list that you want to spend a little more time with. You can even go back at that point and say, oh gosh, I don't remember anything about Bernoulli differential equations. Then you could just go back to maybe you want to watch the lecture again. You could do that. A little example or something. Just kind of remember how that works. But I certainly would not recommend spending any time really looking at the homework. The homework was where we learned and practiced the stuff for the first time through, just to get the hang of it. But at this point, don't mess with the homework so much. I would much more like to see you focusing on the sample tests and maybe the group works. I did mention the group work here because that's not so overwhelming. There's, those are relatively quick to go through. So it's fairly efficient to do that. So I might recommend doing that. Okay, let's see. Try not to just read my solutions to everything. There will be solutions to everything. They are all going to be up there, but I would recommend that you try to really force yourself to work out these problems. When you do the sample final, take it like a real final, right? Try to set aside distractions for a couple hours, just see what you can do. Do the best you can with that, just to get yourself comfortable with kind of what the feeling of the exam might be like. Okay. Yeah, I think just a lot of general stuff. Oh, so the question came up, is there going to be any like extra credits? Are we going to do anything to kind of bump up some scores and stuff? So, for each midterm, there was something to do. I had you watch a video or take a practice quiz or whatever we did. I don't want to give you more to do before the final. I know you're busy, you have other finals and this is a lot to learn. So I'm not going to create work for you that then turns into like extra credit points. Instead, what I'm going to basically do is I'm going to make the exam worth, there's going to be many more points on the exam than what I'm going to grade it out of. So let's just say I'm going to grade it out of 100. There's probably going to be, I have not written the test yet, but I'll probably come up with 120 points of things to ask. And I'm basically going to give you the option to just punt on some things. I mean, honestly, it is a lot of material. I totally get that. In fact, even for me, it feels like a lot. And I could see it being very possible you show up and you look at a problem and you're like, I don't know what I'm supposed to do here, right? I want you to be able to punt once in a while, or at least like, you know, let something go. I say something here about my advice on the exam is there is nothing wrong with skipping over a problem and saving it for later. If you're stuck, you can go on and come back to it or whatever, right? This is really good advice. You should not allow yourself to get so wrapped up in one little thing and spend way too much time on one little thing that you don't have time to get through the whole exam. I mean, I'm hoping that that won't be an issue, but I'm hoping there'll be plenty of time. But yeah, so just so you're wondering, I'm not going to do any extra credit thing, but I am going to make more points available than you will actually have to earn to get 100% on the test. So that's something to keep in mind. Somebody in my first class asked me about Newton's law of cooling and those mixing problems. These were way back. Those were videos you watched even before I met you. That I asked you to watch at the beginning. What I told those guys, I'll tell you the same thing, is if I ask you something about Newton's law of cooling or a mixing problem, which is a chapter 1 application, I'm just going to give you those differential equations. I'm not going to make you memorize those. So those are really old things that we've not used a lot in the recent weeks. So we'll just make that really easy. I don't particularly like asking questions where it's sort of make or break. You either know it or you don't, depending on whether you memorized it or not. I'm not a big fan of that. So I'll tend to stay away from it. On the other hand, I do kind of like the idea of having some kind of real world problem on my test. So that this isn't just totally just dry math all the way through. But we'll see. I have to think about it a little bit. Yeah, and then, okay, so I did have a few, I get so excited, that's my problem. I just like this stuff so much. So I have these extra practice problems here. You can take it or leave it on this. Notice that I did actually put together, so I wouldn't even bother with 6B for sure. This is a 3x3 non-homogeneous linear system, right? So this is a system of differential equations. Here's the A and the B. And I just told you a few minutes ago that I would not ask you a 3x3 example. So I happen to have one here if you happen to be interested in it, but you don't have to feel like you have to do that. Really, there's so much different things you can look at. You're not going to look at nobody is going to study everything. I mean, even if I was going to try and study for my own exam, I don't even know how I wouldn't be able to get through all of it. So you have to pick and choose a little bit, kind of depending on what you feel solid about. Okay, I do have the solutions right here to those problems I just showed you. So those problems do have solutions. Then there is also a review session. And I've got some problems here as well. And oh, look at that first problem. Here, problem number 1, solve. Oh, look at that. That looks like x prime equals something and y prime equals something. That's actually a system of differential equations. And notice I can actually see, do you see how to put that into a matrix? That's what you'd want to do, isn't it? Right, the x prime and the y prime. Here, let me just write this down. Right, so the x prime and the y prime, we could just make those into a column there on the left side. And then do you see how you're actually getting a matrix out of this? These coefficients here, the -1 and then the 2. I could just put that up here in the top. I'll put my x and my y right here. So -x plus 2y. Right? And then on the other equation, I have -2x and 4y. So put that down here. And there's actually a non-homogeneous term, right? There's 54t e to the 3t. right? And there's 9 e to the 3t. Okay, so that very first problem is the stuff we just learned how to do today. Non-homogeneous linear systems. But anyway, there's a few problems here. Some things about transformations, subspaces. Oh, down here at the bottom is some inner product materials, reminding you about the axioms of an inner product. Chapter 5 definitely is going to be worth a little bit of extra time to review. These kind of problems here where you have proposals for inner products and you have to remember those axioms. So again, if that was something, right, like if I had my to-do list and I thought, oh, inner product axioms, I don't think I remember those. I'd put that on my to-do list and then check that off when I have a chance to go review that. Yeah, so then I've got this stuff here. Oh, find an orthogonal basis for, stop right there. Find an orthogonal basis for, what am I gonna use to do that? The Gram-Schmidt process, exactly. So you see questions like that, it's kind of nice to know where it's coming from a little bit. Anyway, yeah, so there's a bunch of stuff here. Here's this one right here, number 9. This is, anybody know what that is?
Bernoulli?
Oh, you're really good. Absolutely. This is from back to chapter 1 because it says y prime. So y prime is the first derivative. It's only a first order differential equation. But on the right hand side, you see the power here. I don't know if you guys can all read that very well. This says y to the 1/3 power. Well, that's the form of a Bernoulli differential equation. So yeah, this is a Bernoulli equation. Yeah, there's just a bunch of practice problems here. It's not obviously totally comprehensive, but there's some stuff to look at there. So anyway, I have that, and then I have typed up all those answers. So in the solutions to all those review session problems, again, if that's something you'd like to practice on, you can also just go through these documents and pick and choose, grab the topics you really need to focus on and let some of the rest of it go. And then the last thing I wanted to point out, I talked about the sample final, the review session, the packet. I want to go over to the pages section of our website. Canvas just won't let me put video links in this type of a folder. But there is a video folder over here under pages that says final exam review session. And I want to point out this is a little different than the review sessions for the midterms. What I actually have are a series of videos that are kind of organized a little bit by topic, but I have to confess they're not very well organized. So what I did to make it a little better for you guys is I sort of wrote a little comment about what's in each video. So like the first video is actually quite long, it's 106 minutes, and it goes back to chapter 1 and chapter 5, which are definitely 2 of the older chapters that probably are worth reviewing, and then a little bit on subspaces as well. So you could turn that on and just check it out if you want. Most of these videos are much shorter, like 24 minutes, 13 minutes, blah, blah, blah. Some of them I actually have a couple of different sections for. Again, you're not gonna probably watch all of this, right? It's just too much watching Dr. Hammond all weekend long. It doesn't sound like a lot of fun to me. So video B, and this just says that what you're getting in these 2 videos, they're both right here, 30 minutes and 4 minutes, is just an overview of chapters 1 through 5. No problems are being solved at all. So if you just needed to review the first 5 chapters, which is really what the first 2 midterms were about, you could just turn that on first, right? And just kind of watch 30 minutes and kind of get that back in your head and then go from there. And then, yeah, there's some other videos here, polynomial based problems about linear independence and subspaces. I've got that. And so on. Yeah, it's just not, one of these days I need to just make my videos a little bit more organized and so it won't be so confusing to jump around. But I mean, it is what it is. It works out okay. Kernel and range of T, right? So if that's a topic that you're still kind of not feeling good about, well, I've got 16 minutes here where you can take a look at that. Oh, I wanted to remind everybody, or I just wanted to mention something on the midterm. The very first problem was a transformation, you know, a linear transformation. This is the midterm that you just took on Monday. And it was asking for bases for the kernel of T and for the range of T. One of the most common mistakes on the entire exam actually was right here. Because the kernel of T, right, so this, I think everybody knows that this is a subspace of V. And the range of T is a subspace of W, right? We do know that. But what I saw is that people were not writing, so the way that you write the vectors for the kernel of T, they have to look like vectors from V. So if V is M2 of R, if V is 2 by 2 matrices, then your kernel of T should look like 2 by 2 matrices. They shouldn't be just written out as like slots. They should actually look like matrices. And the range of T, I think in this problem, it was polynomials, right? Quadratic polynomials. So then down here, my subspace of that was making up the range, this should have looked like polynomials, not just a bunch of numbers and slots. So that people were carrying out the calculations correctly. There was no problem with that. It was just that people kind of represented the answers, not in the format of V and W. So that's a quick comment about kernel and range that kind of comes out of what I saw on that midterm that we just took. So, but anyway, yeah, so there's some video on that. So a bunch of different videos, you can kind of browse through these and see, yep, take it or leave it, whatever you find might be helpful. It is definitely too much stuff to do it all. Nobody would ever ask you to do that. It probably wouldn't even help you to try to do that much. You have to really figure out where it is that you need to spend time. I would go back to my old midterms, particularly the first two midterms, and look at where you had problems or issues with those midterms, and really try to kind of press into that again, see if that can help you out. Okay. Now let me get the lights back up a little bit here. It's out. There we go. Does anybody have any questions about any of the resources? I just wanted to kind of give you a quick little tour there, make sure everybody knows kind of what's available to look at. Yeah, Raylene?
So for the final, is the formula sheet going to be the same as the third midterm?
So yes, I'm going to give you the table of annihilators, the table of integrals. I'm going to give you the Graham-Schmidt formulas. So anything that I gave you on any of the exams, the differential equation for mixing problems or Newton's law of cooling, I'll give you those as well. Yes, I will definitely be as generous as I can because I know there's a lot of stuff. Okay, any other questions so far about any of this? All right, if not, I'm going to take the last part of today's class and give you a quick little idea about how to maybe put some of this stuff together. Let me turn this off. You can get a lot of mileage on your studying for the final by just basically thinking, I'm going to focus on differential equations if you don't mind for this little part of our conversation, but you can get a lot of mileage by just thinking about how to approach differential equations. So I'm going to give you a little roadmap. It's sort of like a little guide or a chart to how to kind of navigate through differential equations, specifically differential equations. Okay, so you know, there's some questions that we can ask. So let's just make a little flow chart here. The very first question, if you have a differential equation and you're trying to figure out how to solve it, the very first question I would ask myself is the differential equation a system? Is it a system of differential equations, or is it literally just a single differential equation? That actually plays a big role in how you're going to navigate solving it. And obviously the answer here is either yes or no. Now, if it is a system, then that means we're looking at chapter 9. So I'm just trying to get you kind of placed in the material. Where is it in the last 15 weeks that we've been together learning this stuff? If it's a system of differential equations, then it's in this most recent chapter 9 material. And of course, today, we sort of bifurcated again into looking at homogeneous versus non-homogeneous, right? So every system of differential equations would either be homogeneous or non-homogeneous. And non-homogeneous is actually section 9.6, which is what we just learned today. And homogeneous is really before that. I'm going to specifically mention 9.4 and 9.5, where you have either non-defective or defective coefficient matrices. So that's kind of a quick little reminder about how chapter 9 is broken down. Now, if the answer here is no, then I would just say go to, we're going to go to question number 2. Okay, so the first question is it a system? If it is, then we can figure out the more recent material tells us what to do. Okay, so far so good?
Yeah.
Now, the second question, let's say that it's not a linear system, which means it's just a single differential equation.
Is it first order?
Here, hold on, it's a little too fast for me. Right, so if I just handed you a differential equation, what would be something about that differential equation that would be really pertinent and relevant that we would ask ourselves right away?
The order of it?
Exactly, Josh, the order of the differential equation. That would be my next question. So the question here would be, what is the order of the differential equation? All right. Fantastic. So this could be, well, there's actually 2 ways to break this down. I'm going to say it could be more than one. Okay, or it could be equal to 1. There's sort of both of those scenarios. Now, if the order is, second order, third order, fourth order, something higher order, then we're really talking about chapter 8 of the book. So at this point, we're just going back a couple of weeks, really. Yeah,
The
Nathan?
exception to that would be if it's constant acceleration, which means you could just, like, remember the gravity and kinematics?
Yeah, that was in chapter 1. Don't worry about that. Yeah, remember the problems about the position, velocity, and acceleration? I'm not going to put that on the file. That was something we didn't do enough with that to really bring that back again at this point. So chapter 8 is really where the higher order differential equations come in. And in this case, what I would do is ask, well, let me first write down what it looks like. Here's what the higher order differential equation looks like. It's just L of y equals F. And what we can do here is we can ask question number 3. So I'm going to come down here and ask question number 3. Can we annihilate the capital F? Right, so there's, another sort of yes or no option here. And if the answer is yes, if we have an annihilator for the big F, then I'm going to be using the Annihilators method. And I've got my table of annihilators if I need it to help me with that. So I would use annihilators. On the other hand, if the answer was no, what's the method that we use when we can't use
Variation
annihilators?
parameters.
Right, variation of parameters, excellent. Write that down as well. So that would be variation of parameters. Okay, fantastic. And then from there, that's about the size of what we need to know from chapter 8. Okay, or at least a pretty good coverage of it there. Now, if the differential, let's go back here again. If the differential equation has first order, right, then we have way back to before I draw that, not quite ready for that. I need to write chapter 1 here. At this point, we're going back to chapter 1. Remember, guys, this is an overview of differential equations. Chapters 2, 3, 4, 5, 6, and 7 are all about linear algebra. So this is focusing on chapters 1, 8, and 9 right here. And I'm gonna talk about what to do in the chapter 1 scenario here in a moment. Question?
Oh, no, it's an answer.
Oh, hold on. Hold on. I'm gonna put 4 spokes here. Anybody know why I'm putting 4 spokes there? Does anybody besides Nathan know why I'm putting 4 spokes there? How about besides Josh? Anybody else want to try it? 4 types of first order differential equations. Do you remember from the first midterm what they were? Matt?
Linear, Bernoulli,
Linear, Bernoulli. What did I hear over here? Separable, exactly. Separable, linear, Bernoulli. Does anybody know the last one? Alexander? Homogeneous, that's right. That's right. That word gets overused. It's overused way,
Of degree
way too
0.
much. What's that?
Of degree
Of
0.
degree 0, yeah, that's right. So it's not the same use of the word as what we have up here, right? It's a kind of a different implication. Let me just take a quick minute and write down, because since chapter 1 was so old, I think maybe taking a moment to write down a little bit about those 4 types again might be useful. There's a little bit more in the way of memory stuff here in chapter 1, so it's worth kind of getting it back in our heads again. A linear differential equation has a very specific form, right? So we would have y prime, and then it's plus p of x times y equals q of x. This is the form of a linear differential equation. So I'm skipping over separable, by the way. Separable just means you can put all the x's on one side and all of the y's on the other side and just integrate it. I want to focus more on the ones that we have equations that we have to learn. Does anybody remember the main tool that we use to solve? Anybody remember one of what the main tool is that we use to solve a linear differential equation? Do you remember back to January? It's just
I is equal to e to the integral of ps.
oh my gosh, that's the perfect equation. And what is I called again? Can somebody help him out? Go ahead.
Integrating factor.
Yeah, this is the integrating factor. I actually love your enthusiasm. I really do. You know, having students that are really excited about this stuff really turns me on as well. So I appreciate it. So yeah, this is called the integrating factor. And so we take e and we integrate p of x in the exponent. And then the other thing that's important to remember, probably equally important, is what happens, or how does the integrating factor lead us to the solution to the differential equation? And the answer is that it turns into a product rule of I with y, and that equals q of x times I. Okay, so you multiply the q of x on the right hand side times I, and that becomes the derivative of the product rule of I with y. So that is on the well, that is how you're going to isolate y. Now you just have to integrate both sides and then divide by I. And that's how you solve for y. So again, maybe you're making a few mental notes. Oh, this is something from 4 months ago. I better review it. It's been a while. While we're on this topic, let's talk about Bernoulli differential equations real fast. They are very similar. So whoops, I've got that started off poorly. The way that a Bernoulli differential equation looks is y prime plus, and can you put that away, please? Y prime plus p of x times y. So the left side is exactly the same. On the right hand side, we have q of x times y to a power. So this slightly different than a linear equation. The big difference is the y to the n over here. And what you're going to need to know here, guys, is you're going to need to know a couple of things. you need to know the change of variables. There's a conversion that we do to turn this equation into a linear one. And the formula for the conversion is very important to know. This is it right here. U equals y to the 1 minus n. Worth memorizing that. And the new differential equation is also worth memorizing. It's very similar to the original differential equation, but we have this factor of 1 minus n that gets multiplied by both the p of x and the q of x. So this is the new differential equation, and you may remember that a Bernoulli equation always becomes linear. A Bernoulli equation always becomes linear. Okay, great. So it's basically these boxes up here, guys. These are all things that are kind of worth knowing. Questions about that? Okay, and then finally, let me say a quick word about the homogeneous one. So this is all chapter 1. We're talking right now about chapter 1 over here. For homogeneous differential equations, these are equations where you can actually solve for y prime as some expression involving x's and y's. And this is the one you might remember, again, this goes way back to the start of the semester, where everywhere you see an x, you replace it with xt, and everywhere you see a y, you replace it with a yt. And if you do that, and all of the t's just cancel out, then it's homogeneous. So, an example of this might be, I don't know, y prime equals x squared plus, well, let's just say x squared over x squared plus y squared. That would be an example. Like everywhere you have an x or a y, you attach a t. So you'll have 2 t's on top, 2 t's on both of these terms on the bottom. They just cancel out, right? So something like that would be an example. And in this case, when you have a homogeneous differential equation of degree 0, there is also a change of variables, but it's usually written like this. Y equals xv is the important equation for that. And because you see y prime right here, you will need to know the expression here for y prime, which just comes from the product rule. So you get xv prime plus v. Okay. So there's and then this always converts when you plug all of that in. You always end up getting something that becomes separable, right? So homogeneous equations always become separable. Bernoulli equations always become linear. Okay. This is a decent review of the first 2 weeks of the semester, actually, right here. It took me 5-10 minutes to do it, but of course, practicing it and kind of really getting solid enough on it will take a little bit more time, but you'll get practice in the sample final. You'll get practice if you go back to the group works, all that stuff is there. Any questions about that? So this roadmap, I guess you could call it like a flow chart, so to speak, is really kind of helpful. I use it for myself to just kind of figure out, okay, I have this question. Where in the material does it belong? What does it fit with? Okay, so it's something good to keep track of. In fact, I think it's such a helpful tool and a good thing to. So a lot of times people know all the tools, but then they just don't know which tool to use when. Like when are they supposed to use which technique? So I put together one last group work. We're not actually going to do it as a group work today. So I don't really have enough time, but I'm going to pass this out. This is group work number 16. And this is just a chance to look at some differential equations and think about how we would solve them. Focus totally on differential equations. And if you go to the Canvas webpage, all of the solutions to all of these problems are there. In fact, I've actually solved all of the differential equations, but we can just look at these and kind of have an idea of how we would solve them. Now remember that sometimes you have to do a little bit of algebra first. So like if I look at the first one, is everybody with me? Let's just, we're not gonna get through all of this, I just wanna look through the first one. The first one, is it a system of differential equations or is it just a single differential equation? The very first problem on the handout. Is this a system or is it just one differential equation by itself here? Yeah, it's just one, right? It's just one differential equation. Okay, so we go to question number 2. What is the order of that differential equation? First order. Okay, so first order, so then it's chapter 1. Okay, so then we have to figure out, well, is that thing separable, linear, Bernoulli, or homogeneous? And so we kind of talked about it here. You have to do a little bit of algebra, but this one is basically going to be linear. So you can pretty quickly work that out. You have to rearrange it a little bit, obviously, to get the y prime figured out and get it kind of isolated, but it turns out to be linear. What about the second one? What about part B?
System.
That's a system for sure. In fact, it's a non-homogeneous system because there's a e to the negative t and there's a plus 1. So this is the stuff we just learned today, section 9.6, a non-homogeneous system. That's how we would solve that one. What about the third one? Sine of y over x times x y prime minus y equals x times cosine of y over x. Any thoughts about how that could be solved? Alexander? Yeah, it's actually a first order differential equation, and it sure looks like it's homogeneous. Like if you attach t's next to all of the x's and y's here, if I put a t there and there, it just cancels, right? If I put a t here and here, it just cancels. If I put a t next to each of these x's and y's, it cancels with the one over there, right? So it's basically, it's all gonna cancel out at the end of the day. So this is homogeneous. By the way, in case you're wanting sections for these, the linear differential equations is 1.6, homogeneous is in 1.8. Part D, let's see, part D, is that one differential equation or a system? One differential equation. All right, so the question is, what is the order of that differential equation?
Second.
It's second order, which is more than one. So we're in chapter 8. So we have our linear system, or we have our linear equation. And so it says, ask question number 3. Question number 3 is, do we know how to annihilate, in this case, it's e to the 4x times the cosecant of x?
No. That's one over sine.
I mean, you can look at your table. If you look at the table of annihilators, you say, is there a cosecant of x in that table anywhere? And you'll find out that there is not. So the answer is no, we don't know how to annihilate it. Okay, so we must have to use variation of parameters. Okay, and just for reference, that's in section 8.7. Part E, let's see, is that a system or is it a single equation?
Single.
It's a single equation, and what is the order of the differential equation in part E?
Third order.
It's third order, okay, so that means we're back at chapter 8 again. So we go to the third question. Do we know how to annihilate 2e to the negative x divided by 1 plus x squared?
No.
I don't think so. I don't know how to annihilate it, but actually there's another problem here. Because the differential equation is third order, and do you remember for variation of parameters, what order did we learn about? Only second order, right? So actually this is a trick question. I promise I don't do trick questions on my exams, just on the group works. So this is impossible, right? This one, there is no way to solve that one.
Is it actually impossible? Or just for
No,
the
no,
class?
it's impossible for us
Okay.
because we didn't really learn it. But no, we could do it. You could use a higher order version of variation of parameters. And finally, I'll let you guys look at the last one. That one is also linear, so we have another linear equation there. And so if any of you are interested in practicing in more depth, of course, you can study those and take a look at them and learn a little bit about them. Well, we have only a couple of minutes left, guys. I want to do a couple more things. I just have two things to wrap up. First thing is, I just want to say to all of you, thank you very, very much for taking my class. I absolutely love being here Mondays and Wednesdays. I hope that comes through. I know it's been a little tough. We've had all this stuff with, having to start remote and then hanging in there, coming in virtually. It's been a little difficult, but I have really been happy to see people again. And if you guys didn't sign up for my class, I wouldn't have the joy of doing this. And I really want to thank you for taking the time to take my class. And I hope it's been a good experience for you. By the way, that reminds me, you still have until Friday to fill out an SOQ form for the class. If you want to give the class an evaluation, I really encourage you to do that. Second thing is, I always like through the years, and I haven't been able to do this for the last couple of semesters, but I always like to sort of remember all of the people whose minds I have poisoned through my profession over the years. And so I always like on the last day of class to take a class picture. With myself included, that I have some beautiful stuff on the board here. I'm wondering if I could grab everybody to kind of come up and we'll get real cozy so I can get a picture. I'm going to grab somebody to take our picture, okay? So come on up to the front, take a quick picture.
Mr. President is like the help of my class.
Yeah. Come on up, guys. Let's get really, really tight. I've got a couple people to take our picture. Thank you, guys. You can stand maybe way back there in the center or so. You just have to let us know. Let us know if we're. I'm gonna be sitting right here. Come on in closer. We'll make a second row. You guys can get down low, and we'll see if we can get everybody tight. Can you see everybody? Yeah. And you can leave your mask on or take it off, whatever you want to do. I'm gonna take mine off.
How dare you? All right, everyone. 1, 2, 3.
Thank you.
No worries.
Solomon, did you get it? Yeah. Okay, thanks, guys. Really appreciate it. I will send that out to you guys. I will send a picture in the email so we can remember the semester. Can you just send me an email? Thank you so much. Thank you so much. Really appreciate it. That's fine. Thank you so much. Guys, have a great day. Study hard. And we will see you again soon.